Mountain grades of 3% don't sound extreme until you're pulling 10,000 tons up them. At that angle, gravity exerts a constant backward force of over 600,000 pounds trying to drag the entire train downhill. The locomotive must overcome not just rolling resistance, but this massive gravitational load while maintaining steady speed. In winter conditions, with ice on the rails, the challenge becomes even more severe. Yet freight trains climb these grades daily, hour after hour, without drama or failure. The locomotive doesn't strain or struggle visibly. It simply delivers exactly the right amount of power to each wheel, adjusting thousands of times per minute. How is this level of precision possible with something so massive? The story of locomotives begins with steam power, a revolutionary technology, but one with severe limitations. Early steam locomotives relied on direct mechanical drive systems, where expanding steam directly pushed pistons connected to drive wheels. These machines required massive boilers, constant water stops, and delivered relatively poor efficiency, converting just a small fraction of their fuel into useful work. The real breakthrough came in the 1930s with the introduction of diesel-electric systems. This innovation fundamentally changed rail transport efficiency, allowing locomotives to operate for days without refueling while delivering consistent power across all conditions. Looking at key milestones, the EMDF-7, introduced in 1949, became one of the most successful early diesel-electric locomotives, helping to end the steam era. The 1990s saw the introduction of AC traction motors, providing superior control and efficiency. By the 2000s, sophisticated computer control systems transformed these machines into rolling data centers, constantly optimizing performance. What's fascinating is that despite tremendous technological advances over a century, the core challenge remained unchanged: how to effectively convert fuel energy into controlled wheel torque on steel rails. Modern locomotives represent the pinnacle of this evolution, producing between 4,000 and 6,000 horsepower while weighing just 200 to 220 tons. An incredible power-to-weight ratio that enables them to move freight with unprecedented efficiency. To understand how modern locomotives truly function, we need to recognize that they operate on a principle fundamentally different from automobiles. Forget everything you know about transmissions, clutches, or direct mechanical connections between engines and wheels. Yet those simply don't exist in modern locomotives. Instead, these machines integrate four fundamental systems working in perfect harmony: the prime mover, the diesel engine, the main alternator, multiple traction motors, and sophisticated control systems. Together, they form what is essentially a mobile power plant feeding electric motors. Think of a locomotive as an electric vehicle, but one that generates its own electricity rather than storing it in batteries. This creates a dynamic balance where power generation must precisely match traction demands in real time across constantly varying conditions. And let me be clear, there's no magic involved. Just precise electrical engineering and computer control. The genius lies in how these systems integrate to transform diesel fuel into the massive pulling power required to move freight trains weighing thousands of tons across continental distances. At the heart of every diesel-electric locomotive sits the prime mover, typically a massive 16-cylinder diesel engine. Unlike car engines that constantly vary their RPM, locomotive engines operate at relatively constant speeds, optimized for electrical generation rather than variable speed operation. When the engineer calls for power, the diesel engine doesn't spin faster. Instead, it delivers more fuel to maintain its optimal RPM while generating more electricity. This electricity flows to the main alternator, essentially a massive generator directly coupled to the engine. Modern locomotives primarily use AC traction systems. While older locomotives use DC traction motors, AC systems provide superior torque control, especially at low speeds, and enable regenerative braking capabilities. These advantages make AC systems particularly valuable for heavy freight service. The traction motors themselves are engineering marvels. Each one weighs around 5,000 pounds and can produce over 1,000 horsepower at peak output. They work on a straightforward electromagnetic principle. Electrical current creates magnetic fields that interact to produce rotational force. What makes them special is their ability to deliver massive torque at low speeds while operating reliably for years under extreme conditions. Perhaps the most sophisticated aspect of locomotive operation is wheel slip detection and control. Every locomotive axle is equipped with sensors monitoring rotational speed thousands of times per second. The control computers compare these readings to track speed and other axles. When a wheel begins to slip, the system can reduce power to that specific motor within milliseconds, often correcting the slip before the engineer would even notice. The control system's job becomes even more impressive when you consider that it must balance power across 4 to 6 traction motors simultaneously, each experiencing different adhesion conditions. In modern locomotives, these adjustments happen far too quickly for human intervention. The engineer simply sets the desired power level, and the computer handles all the complex power distribution. The level of integration between systems is remarkable. When a locomotive climbs a grade, sensors detect the increasing load. The engine governor increases fuel delivery to maintain RPM. The alternator produces more electricity, and the traction motors receive precisely calibrated power, all automatically adjusted thousands of times per minute. To truly appreciate locomotive engineering, we need to understand the scale involved. Consider a typical freight train weighing 15,000 tons climbing a 2% grade. Basic physics tells us that gravity creates approximately 40 pounds of resistance per ton for each percent of grade. That means our train experiences about 1.2 million pounds of gravitational resistance, in addition to normal rolling resistance and air resistance. Overcoming these forces requires tremendous power applied with precision. The physics of steel wheels on steel rails creates both advantages and challenges. Yet the steel-on-steel contact provides very low rolling resistance, about 1/10 that of rubber tires on asphalt, but also limits adhesion. Locomotives can only apply force equal to about 25 to 30% of their weight before wheels begin to slip. This adhesion limitation explains why heavy freight trains often need multiple locomotives. A single modern 6,000 horsepower locomotive weighing 210 tons can apply maximum tractive effort of around 60,000 pounds. For our example, train climbing a 2% grade, physics demands over 1.2 million pounds of force, requiring multiple locomotives working in coordination. This coordination happens through multiple unit operations, where 2 to 4 locomotives link their control systems. The lead locomotive sends commands to trailing units, synchronizing power delivery across the entire locomotive consist. This allows precise power management across thousands of horsepower, all controlled by a single engineer. The efficiency of the system is staggering. Modern freight locomotives move 1 ton of freight more than 400 miles on a single gallon of diesel fuel, making rail transport about 4 times more efficient than trucks. This efficiency comes from the combination of steel wheel efficiency, optimized power delivery, and the ability to move massive loads with relatively little power. Let's walk through how these principles apply in real-world operations. When a locomotive starts its journey, it follows a precise sequence. The cold engine undergoes startup procedures, warming critical systems before applying load. Traction motors are tested, brake systems verified, and computers perform diagnostics on thousands of parameters. As the train approaches a mountain grade, the engineer must implement a specific climbing strategy. Power settings are adjusted based on train weight, grade profile, and adhesion conditions. The engineer must also prepare for what comes after the summit, setting up dynamic braking systems to control downhill speed. Winter operations add another layer of complexity. Locomotives include sand application systems that deposit sand directly in front of the wheels to increase adhesion on slippery rails. Advanced wheel slip management systems become even more critical in icy conditions, making thousands of adjustments to maintain traction. The dynamic braking process represents another engineering marvel. When a train needs to maintain or reduce speed on a downgrade, the traction motors reverse their role, becoming generators. They convert the train's kinetic energy back into electricity, which is then dissipated as heat through massive resistor grids on top of the locomotive. This system can produce braking force equivalent to several thousand horsepower without using the train's air brakes. The most modern locomotives take this concept further with regenerative braking systems. Rather than wasting energy as heat, these systems can feed power back into the electrical grid during braking operations, particularly valuable in passenger and commuter rail applications, where frequent stops occur near electrical infrastructure. Professional locomotive engineers develop specialized skills that extend far beyond simply operating controls. They learn to read grade profiles, anticipating power demands based on train weight and terrain. They manage fuel consumption through optimal throttle positioning and minimizing unnecessary power changes. Maintenance becomes a critical part of keeping these complex machines operational. Traction motors undergo regular overhauls, diesel engines receive service at prescribed intervals, and electrical systems require sophisticated diagnostics. Modern locomotives accumulate vast amounts of operational data, allowing maintenance teams to identify potential issues before they cause failures. When failures do occur, locomotives incorporate robust backup systems. If a traction motor fails, the locomotive can continue operating on remaining motors at reduced capacity. Critical systems have redundancies, and limp home capabilities ensure trains aren't stranded in remote locations. The integration of technology continues to advance. Modern locomotives transmit real-time operational data to centralized monitoring centers, where algorithms analyze performance patterns and predict maintenance needs. These systems can detect subtle changes in electrical signatures, thermal patterns, or vibration profiles that indicate developing problems. There are still operational limits, however. Maximum safe speeds on grades are carefully calculated based on braking capabilities and train weight. Thermal management becomes critical during sustained high-power operations, with cooling systems working to dissipate heat from electrical components and the diesel engine. That 15,000-ton train climbing mountain grades isn't defying physics. It's applying physics principles through precisely controlled electrical systems that adjust thousands of times per minute. The locomotive's ability to deliver exactly the right amount of power to each wheel under varying conditions represents one of the most sophisticated applications of electric motor control in any industry. To me, that's the real beauty of locomotive engineering. Not brute force, but intelligent power management. These machines don't overwhelm challenges with raw power. They solve complex problems through sophisticated control systems and electrical engineering principles refined over decades. Every freight train represents a mobile electrical grid managing megawatts of power, distributing it precisely where needed, and adapting continuously to changing conditions. The fact that this happens without drama or fanfare, the trains simply work day after day. Moving the goods our economy depends on makes their engineering all the more impressive. And now I'm curious, have you ever wondered how those massive trains actually stop? How do air brakes coordinate across 100-plus cars? How does dynamic braking interact with conventional friction brakes? And what happens in emergency stopping situations? The systems that bring these enormous masses safely to a halt are every bit as fascinating as those that move them forward.